You're listening to Worth Electronics' What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Worth Electronic technical specialists. We're going to shine a light on our topics like energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Worth Electronics' What's Up podcast. Well, not so long ago, Thomas O'Brien, he's a design engineer here at Worth Electronic, presented a webinar in which he discussed the correlation between the designing of a transformer and its effect on EMI. So in this podcast, we will look at the transformer's impact on conducted and radiated EMI in an application. Thomas also discusses good EMC design practices and then covers additional EMI reduction measures that designers should be aware of. Enjoy today's Worth Electronic What's Up podcast with Thomas O'Brien and our presentation, Transformer Design for EMC.
Hello, everyone all over the world, and welcome to this webinar today. We're going to be talking a little bit about transformer design, how to best design your transformer and minimize the impact that the transformer will have on your board and on the layout, so that you can have a good pass in the EMC house, which is what everyone likes to see. So today we're going to start looking at, first of all, the transformer itself, what impact it can have on the EMC. Then we'll look at what specifically we should avoid when we design our transformers for EMC. And then we look at some good practices on how to design the transformer so that it limits the impact it can have then on EMC. And then if all those techniques and practices don't work, then we can look at some additional measures we can implement within the transformer then to further reduce our emissions. So magnetic components are at the heart of every power supply, and when we also need to have isolation between the primary and secondary, then we need a transformer. And so the transformer is a vital part of every power supply and a vital part of isolation. But it also brings about some potential problems and some difficulties that can be had with EMC, and maybe people are not so aware of all the different measures that we can implement in the transformer just to help impact or help limit any impacts. So first of all, why do we worry about EMC? Well, one good reason is to think about EMC very early in the design, is that it can have a big impact on the cost, the overall cost of your project. So if we think about EMC at the early stages of design, for sure it costs a little bit more, takes a little bit more time to consider all the EMC issues in the early stages, in the pre-design stages, and then in the prototype stages. But then when we release our product onto the market, hopefully the EMC then at that stage will be sorted. We've looked at all the problems that could arise, and then it's a plain sailing from then on when we go into production and then release onto the marketplace. However, if we don't consider EMC in the early stages and we just start thinking maybe in prototype stages, we might get a little bit faster towards the release to the market, but inevitably often EMC will raise its ugly head in the test house, and maybe even after the product is released, which is the worst case scenario, and then we have a big problem because we might even have to withdraw the product from the market or hold up the release or postpone selling the product in whatever market. So best advice is to consider the EMC in every part of your, especially switch mode power supply designs, because they're noisy by nature. If you don't take EMC into consideration, then for sure you will have some issues in the test house. Then if we want also to sell our product anywhere in the world, then we need to meet certain EMC regulations. Now, unfortunately, these regulations vary a little bit all over the world, and there is some consistency from region to region. The typical frequencies of interest are from IEC standards, which is International Electrical Commission, will be from 150 kilohertz to 30 megahertz for the conducted band. So that's the noise that's injected into the mains lines. Then for the radiated emissions, it goes from 30 megahertz up to 1 gigahertz. Now, the FCC in the US actually only start the conducted emissions testing at 450 kilohertz, which is a little bit higher. But still, if you plan to develop a product that you want to sell all over the world, then you need to consider whatever standard is applicable to that region. So there's big variation. Even the limits are varied from region to region, from standard to standard, and also Class A or Class B. So Class A is typically for in industrial applications, and Class B limits, which are a little bit severer for conducted and radiated emissions, but a little bit less harsh for immunity, are different for Class A and Class B as well. So we need to know our marketplace, and we need to know the limits before we start our design. Now, let's look at the transformer itself. So in the ideal world, our transformer has just one parameter, I guess, and that would be inductance. We have a coil wrapped around some core, and we have a primary side, and we have the same on a secondary side with some turns ratio to give us whatever voltage or current we require. And in the ideal case, we just have primary inductance and a secondary inductance. But I think we all know that the world we live in is far from ideal. It's not just engineers who know that. And so we need to consider actually all the parasitic elements as well. And so what are those parasitic elements? Well, we have, first of all, resistance in the windings. So obviously, if we have any length of copper wire, there's going to be some resistance, and we do on the primary, and we have the same on the secondary. So we have resistance of each wire. That's just one of the parasitics. Then we have another parasitic called leakage inductance. So when we have a transformer, not all the primary and secondary will be perfectly coupled, and there's some imperfect coupling is called leakage inductance appropriately. So that inductance is inductance that doesn't couple with the secondary, and it shows up in series then with our primary winding, and can cause some issues both on the circuit. We need to we have in a flyback, we have a higher spike caused by this leakage inductance, and we need to add a snubber circuit to reduce that so we don't damage our MOSFET. But also the ringing following on from the leakage can cause some issues with conducted and even radiated if the ringing frequency is high enough. So we need to be aware that leakage is there, and we need to have measures to deal with it. Then we have another parasitic called the intra-winding capacitance. So this is the capacitance from turn to turn, and the sum of those turns is called this intra-winding capacitance. So it's the capacitance distributed on one single winding. So on the primary side, we can measure the capacitance just across the winding itself, and that will be the intra-winding capacitance. And that can cause some issues, particularly on turn on. We get a spike caused by this capacitance, and also the capacitance, say, in the MOSFET switch, and that causes a spike. And again, everywhere you have a spike, you'll have some ringing that follows on from parasitic capacitances and inductances in the circuit. And we have the same capacitance then on the secondary side, intra-winding capacitance. Then what's very important for transformers is this last one we'll look at is called interwinding. So the interwinding capacitance. So that's the capacitance between the primary and the secondary. So you can imagine in any transformer we have a layer of primary, and then we have a layer of secondary on top or underneath, and these act like parallel plate capacitors, and then that gives a parasitic capacitance, which allows current then to flow from the primary to the secondary. And that current then has to find a way back to Earth, and then that can show up then as peaks in the conducted emissions. So this is the one to watch for, and we'll look at this in a little bit more detail later on. So again, we have we look at a little bit more detail, as I mentioned, about this interwinding capacitance. This is a big problem in the conducted emissions. So the conducted emissions I mentioned before are typically from 150 kilohertz to 30 megahertz. And one of the biggest problems is when the current, particularly the common mode current. So common mode current is actually current that flows along both primary. I would say they have a plus here and a local ground here. So the common mode current actually current flows along those two wires simultaneously, and it's referenced to Earth. And when we have a capacitor here, that's common mode current is related to the switching frequency, and then harmonics of that. It can pass through this parallel plate capacitor that we have there, this parasitic capacitance, into the secondary. And of course, current always flows in loops, so it has to find a way back to the source, which is typically the neutral, and neutral is often connected or usually connected to Earth, and so it can find it will find a way back to the source. And that secondary sometimes is actually connected directly to an Earth on an application, or if not, it will find a way back through capacitive coupling to Earth, because high frequency, we don't need very much capacitance for it to find a way back at typical hundreds of kilohertz switching frequency. But of course, that's only half the story. A transformer also is a long wire wrapped around in a coil, and then we have high turn-on speeds, switching speeds passing through that, and so you get this high frequency going through a coil, a long coil of wire. What is that? Yeah, it's an antenna. And antennas, of course, can transmit radio waves out. So we're looking at 30 megahertz plus here that will be radiated out into the air in both E fields or electric fields and H fields. So the E field is primarily related to high voltage or high dV/dt changes in voltage, which we get when we turn on and off the switch. And then this H field is related to high changes in, or high IDT, or changes in the current. And both of those are radiated out into nearby components and critically into the cables. So every application needs, well, unless I guess it's wireless, but it needs input cables and output cables, and these can be quite long, and if we have radiation that's coupled into them, then that's not good. Also can be radiated into external circuitry, and in the worst case, where we don't have very, say, good signal to noise ratio, it can actually interfere with external circuitry and then cause problems for other circuits, radiated again into the PCB traces and basically everywhere. So we want to avoid these emissions, or at least minimize them as best we can. Then here we look now at a typical switching signal. This is actually from a flyback circuit. So here we have the voltage across the MOSFET, so the V drain to source voltage. And we can see here when we turn on the switch, we basically have no voltage across the MOSFET. Then when we turn off the switch, the voltage swings back up to a high level. This level here is actually a function of this leakage inductance I talked about. The higher the leakage, then the higher the spike will be. And that's ringing then with the output capacitance of the MOSFET to get this this ringing here. So we typically have to dampen this, or this voltage spike can go extremely high. And we dampen that with a snubber circuit. You can use resistor capacitors or resistor capacitor diodes, or even Zener diodes to dampen this, but it all eats into your efficiency. So if we can reduce leakage, we can increase the efficiency of our power supply. Then, yeah, that's the voltage side of it. Then we have the current. So when we turn on the switch, as I said, we have no or very little voltage across the switch, but we have our full voltage across the winding of the transformer. So the current will rise linearly up to a certain point, and then we switch off, and then the voltage, as I mentioned, will swing back up. You can see as well, when we switch on, we get this little voltage spike here, and that's actually a function of the interwinding, so the winding to winding capacitance. So the higher that is, then the higher this spike can be. And if we can zoom in on that, then we'll see that there's actually some ringing as well, which can cause problems for your radiated because of the high frequency of that. But when we look at the noise distribution from this power supply, or from on a spectrum analyzer for an EMC analyzer, and we look from the typical frequency ranges from 150 kilohertz up to 30 megahertz, we can see these characteristic peaks here. And so in this case, the fundamental frequency was 116 kilohertz, but then every multiple of that, so every harmonic of that, we can see a peak from that. So we at twice the switching frequency, we 232 kilohertz, we get a peak. Then 3 times we get a peak, and all the way up we can see these peaks quite clearly up to about 5 megahertz, where it starts to get a little bit harder to see them. It's not that they're disappearing, they're still there, but it's just a function of how the logarithmic graph looks, and also how the EMC analyzer looks at these voltages. So if we were to zoom in or look at it in more detail, we'd still see these peaks, but they're not so obvious from the graph. And what is this? This is just basically a practical demonstration of Furrier's theorem, which says that you can make up basically any periodic wave with a sum of weighted sinusoids. And this is exactly what this is. So this this voltage signal and this current signal can be made up basically of the sum of all these noise signals. Of course, there's some filtering and stuff that changes this, but it's more or less a demonstration of Furrier's theorem. Then if we notice up in the higher frequency, so here this peak at around 17 megahertz, so this is actually typically caused by a resonance in the circuit. So somewhere maybe on the layout or in the cables, there's a parasitic inductance and capacitance somewhere, and then we have a very low impedance, which is letting some of that noise show up then on the conducted emissions. So all these, in this case, we're below our limits. This is the peak, the quasi-peak limit, and this is the average limit. But yeah, it's always nice to have a little bit more margin. So that was the conducted emissions. Then we have radiated emissions as well. So the radiated emissions are usually from higher frequency, usually turning on and turning off. of the switch, and because we have very, very high slew rates, so the VDT and the IDT rates are quite high. And once we have those, we always get spikes and then some ringing. So we zoomed in on the ringing here, and that ringing, if you measure the frequency, will more than likely show up as a peak then in the radiated spectrum when we do our open area test site, or we go to a shielded chamber where we can do this radiated emissions testing. And so radiation, it also needs to be controlled. How can we reduce the radiation? Well, we can do some things like slowing down the slew rate, or the on time and off time of the signal, and that slowing down of the off time will reduce the high frequency harmonic content in the signal, and then hopefully reduce the signal. But of course, it comes at the expense of a little bit of efficiency loss. But I guess a small drop in efficiency is a small price to pay for a pass in the EMC chamber. So another way we can help reduce these is, or basically filter them out with small ferrite beads, or even SMD resistor can help, or with the small inductance in it can actually filter out some of that. So we can put those in series with the current ringing there, and that can help filter them out. But again, at the price of some efficiency loss in the circuit. Now we'll look at some things that we should try to avoid when we're doing our transformers. So one technique that people sometimes use with transformer design, specifically when safety is involved, is these things called flying leads. So what are flying leads? So if we look at this transformer here, we have a primary winding typically connected to some pins here. And on a transformer where we don't have flying leads, the secondary will be connected typically to the other pins on the other side. They're missing on this one, this particular transformer. But when safety is involved, we often use a special insulated wire called triple insulated wire, or we can use fully insulated wire, FIW wire, for some safety standards these days too. And that's special wire with several layers of insulation, which actually meets and passes several safety standards. So if we use that on the secondary side, and then we have these leads flying along, we can get very high creepage and clearance distances. So this transformer would be assembled, and then the flying leads would be manually placed into the board at some point far away from the transformer. So the flying leads can be seen as a really clever way and space-saving way to achieve high safety, but it comes at a cost, because we have our secondary high currents usually flowing in these wires with some ripple currents in them, and they make fantastic antennas. Also, how these flying leads are placed on the PCB, as I said, it was usually done by an operator and manually inserted into the holes. So there's no control over how these leads will lie. And so every time you do an EMC check, then you try a different board, and the wires will be placed in maybe a completely different orientation, and that will give you basically a totally different set of results. And so you have no control really over the EMC output from the power supply. So basically, that is enough said. Flying leads are not a good solution as far as EMC is concerned, so we should try to avoid them. Another thing that we should try to avoid is basically this type of core construction. So this is called an EI core. Maybe fairly obvious why it's called EI. So we have this E core here, shaped like an E, and then we have this eye core here, shaped like an eye. And these two are joined up to make a complete core. And of course, you'll have your windings then wound on a bobbin inside of this core. Often when we do a transformer or all inductors, we need an air gap. The air gap is used to store energy, but that air gap has very, very high magnetic fields around it. Now, if we were to use this shaped core for a transformer where we need an air gap, so a flyback is an example of a transformer where we need an air gap. So we store the energy when we turn on the primary side in the air gap, and because of that, there's a very high magnetic field around this air gap. So how do we do an air gap with this type of core? We usually put some tape, mylar tape, or some plastic tape of a certain thickness in between or attached to the eye leg. And so this makes up actually 3 discrete air gaps, and that's how we do the air gap with this type of core. Now the problem with this is, as you can see, that this air gap is actually on the kind of external surface of the transformer. So if we have any components here or on this side, then there'll be a very high H field close to them. The air gap there's some leakage of the flux around the air gap, which tends to spread out into those components and can cause some problems with the EMC. And so this type of construction should be avoided if we can. Then what can we do to improve the EMC in our transformer? And one of the reasons, so when we need, or one of the things we can do when we do need an air gap is, rather than having an air gap distributed equally on all the 3 legs, we can avoid putting the air gap on these legs. So naturally we do have a very, very thin air gap. We have 2 separate core halves and they have to be joined together. So there will be, by nature, a very, very thin air gap here. But because it's so small, we can almost neglect it for its impact on the EMC. Instead, we do our air gap, or Miller air gap, only on the center post. We can do it either on just one half. When the air gap is small, that's fine, or if it's a very big air gap, sometimes we'll do it on the 2 leg halves. But in this configuration, then the gap is at the geometric center of the transformer, and so it'll be furthest away then from all the surrounding circuitry. This fringing flux and is farther away from all the surrounding circuitry, and also we have all the windings which kind of shield it from the external circuitry as well. And so for EMC purposes, this internal center leg gap is by far the best approach when you need an air gap in your transformer. Now, let's look at one, I guess, fundamental basic of transformer design for good EMI. And what is it? Basically, build as small a transformer as possible. Why does the size, a reduction in size, help you with your EMC? Well, basically, you have much less parasitics. When you have smaller transformer, you have shorter cables, usually smaller leads, smaller air gaps, less parasitic capacitance in there, just as a function of the size, and then less leakage inductance too. But there's a little bit of a problem with that. How do we normally achieve a smaller size transformer? I mean, I can't hear anybody talking at the moment, but I hope some of you are saying increase the switching frequency, which is exactly the correct answer. But of course, increasing the switching frequency is bad for our EMC. So, like everything in the engineering world, it's about finding a good balance between the two. So but try to keep the transformer as small as possible as a general rule of thumb. So now let's look a little bit more specifically at the parasitics and the problems that they can cause. So I mentioned before, this interwinding capacitance is really a killer for our EMC. If we look here at this transformer, we can see we have a primary winding, and then we have our secondary winding. This is like a typical construction, and we have some insulation barrier in between, which is often just layers of tape or some paper tape sometimes. And what does that look like? Yeah, it looks like a parallel plate capacitor. So we have this copper, so it can be seen as a conductive plate, and this is all copper as well, another conductive plate, and they're both in a parallel configuration. But if we can imagine these are wound in a circle around a core, so the plate is actually quite large because it forms a whole huge loop, and so we actually end up with quite a large capacitance. So if we look here at the formula for parallel plate capacitor, and we can start to intuitively see maybe ways we can reduce that capacitance. So we basically have three parameters we can play with here. We have this epsilon r, which is the relative permeability or permittivity of the dielectric plate in between the two plates. The higher that is, then the worse it is for our capacitance. The best thing to have in there is air, as the relative permeability of air, or more precisely a vacuum, is 1, which is as low as we can get. Then we have the area of the plates, so essentially this distance here by this distance here. Increasing the area increases capacitance again, and then reducing it reduces. And then we have finally this third parameter, the distance between the two plates. So these are the parameters we can play with to reduce our capacitance. So how can we actually implement that then in a transformer to reduce the capacitance? Well, one way we can do it is to use a narrower bobbin. So we have the transformer here, and the bobbin winding width is from here to here. So if we actually move this wall, say, of the bobbin closer here, then we essentially reduce the this area then between the windings. So that's one way. An even more effective way is to actually completely split the primary and the secondary, and by using a multi-section bobbin. So we can see here we have a multi-section bobbin. So we have a primary on this side and a secondary on this side, and you can see that then the area between the primary and the secondary then is very, very, very small in that scenario. Another parameter, then we can increase this distance. If we look here, the distance is on the denominator. So if we increase that, then we will reduce the capacitance. A simple way to do that is by increasing the number of, or the thickness of the tape, or the number of layers of tape we have between the primary and secondary. So we can see when we double the tape, the thickness of the tape, then we reduce the capacitance by half. So it might seem like a very small change, but it really can have a big impact by increasing the number of layers of tape here. But again, we have to be careful, because both of these reductions in capacitance will increase our leakage. And our leakage, as I mentioned before, can have a big impact on the efficiency of the transformer, and also can cause some EMI problems as well due to parasitic ringing. So yeah, we can easily, I guess, reduce the capacitance, but then it comes at the cost of increased leakage. The final parameter is this epsilon r. We can also reduce this by using very low dielectric varnishes, or in the case of potted transformers where we use potting compounds, or even better, to actually have no varnish or potting compound, and then we get our epsilon R down to 1, which is as low as it can go. And so we do have to consider that the tape we need some insulation there, so we probably have to have some tape, but still, by not using a varnish or potting compound or using very low ones, we can reduce this epsilon R and hence reduce the parasitic capacitance. And the bonus about this technique is it does not affect the leakage inductance, so it's a win-win. Now, there are other things we can do as well for the transformer. So if we look here at a typical, looking at a flyback in this case again, look at the circuit here on this side. We have a very noisy node here, this switching node, and this is always the biggest source of EMI noise in a switch mode power supply. So we can see we have this high voltage switching here, so very high DVDTs. Also, we have all the current passing through this loop here from the input capacitor. So this whole loop is a little bit noisy, but this node really is the killer for the EMC. If you ever are playing around with a sniffer probe, so a little probe that can look at the noise on a switch mode power supply, and you zoom into the drain on the MOSFET, then you'll really see your noise going crazy when you put it up around this node. So this node, being the highest source of noise, is the most important one to control. So we can see here on a typical transformer how we should actually wind it. So we have here this noisy node connected to the switch, and we have this very high DVDT on this node. However, on this node, on the transformer, this is connected to V bus, which is a constant voltage. And so it's relatively stable voltage and not particularly noisy. So this would be this node on the circuit up here. So it really makes sense to start, if we're doing a winding like this, our primary, as the very first winding. So the first wind here, this noisy node on this part of the transformer. Why? Because if we look at this primary secondary barrier here, where we have the tape between the two windings, we can actually see we have a quiet node here, and it gets a little bit noisier because the DVDT, the net voltage differential, increases as we go down to the noisy node. So we actually have quite a quiet node here, and this is at the barrier, but we have a very noisy node here. If we were to do it the other way around, then we have a very high DVDT just at the barrier, and that is not good. So that noise then, the higher the net DVDT, the more noise current can be injected through this barrier in this interwinding capacitance into the secondary. And if that's injected into the secondary, then as I said, it will find its way back to the source and earth, and then show up as noise on the conducted emissions path. So keep the quiet nodes close to the barrier is the message from this winding. It's a very simple technique, but not always followed, as I have seen on many transformer designs, or at least when customers come, and they often have this switching node up here. But if possible, then always try to keep it as far away from the barrier. Of course, we need a at least two layer winding to implement this. If it's just a single layer primary, then it's not so possible. But anywhere where we have more than one layer, then we should always keep this noisy node away from this barrier. Also, these lower voltage windings then, because this noisy node is the very first winding, these lower voltage windings, the secondary, and if we have any low voltage AUGs, they will act like a kind of a shield as well, and shield this noisy node from the outside world, which will help a little bit with radiated emissions. So nearly always makes sense to start the primary winding as the very first winding. Now, say we've implemented all those techniques and we still have an EMC problem in the lab. Is there anything else we can do? Fortunately, the answer is yes. There are a few things we can do. Of course, they do come with some negatives. Typically, cost or size are the problems. So one thing we can do is we can add a copper foil shield directly between this primary secondary interface. So this is a shield wire is typically a foil, a very thin copper foil. So we should always make sure it's very, very thin copper foil to reduce eddy current losses in that. And also very important when you're winding these shields is not to connect one end to the other. So you need to isolate the start end from the finish of this end, or else it will actually be a one-turn winding, like a short circuit, and short circuit the whole transformer. So, and that's not a good thing. You will get a very hot transformer. So important to shield it, and I use a very thin shield when we're doing this. And what this does is it picks up these high DVDTs, capacitive currents that are injected in, or that could be injected into from the primary to secondary, and it provides a path back to the primary side without it actually going into the secondary. So you actually get this kind of closed loop on the primary and stopping those noise currents from getting injected into the secondary. Now that shield obviously needs to be connected somewhere on the primary, so you typically have a wire soldered on somewhere on the shield and will be connected to a quiet node on the power supply. So we look here, you can connect it to the V bus, which is fine because that's a quiet node, or connect it to your local ground, which is also a quiet node, not to the switching node there, which is the noisy one. And that can have a very, very good impact. If we looked here at a 20-watt flyback transformer that I tested with, first we looked at the noise without the shield, which is the orange signal here. So you see we were quite a bit over the average limits here. And then when we apply this so-called Faraday shield, this shield between the primary and secondary, then we can get you can see a reduction of between 5 and 10 decibel microvolts in quite a lot of the frequency spectrum, all the way up to here. That maybe this resonance is affected, so it's actually gone up a little bit at the end there. But yeah, often this area can be quite troublesome to pass, and it does a very good job for this lower conducted emissions region. Now that shielding technique is a very manual process and a little bit expensive to implement, even though it does have quite good results. So there are other ways where we can make that a little bit cheaper, maybe not having such a good impact, but giving a similar effect. One of those is by using a wire wound shield. So basically we do the same thing. We have a primary here and our secondary here and the barrier. And instead of actually having a copper foil shield, we wind a layer of wire, usually very thin wire. So we have very good copper coverage of the whole layer across here. So it actually, from the primary side, it looks like a shield wire when it's just a very thin layer of copper winding. And then one way to finish that is to bury the end of that shield in between some layers of tape. That's not the most optimal way because, again, it's typically a manual process. Of course, we need to connect the other end to the primary side to one of our quiet nodes, so ground or V-bus, and then the other one is left floating. But if it's possible, an even more efficient way, and this can be implemented fully automatable in a typical production process, is by winding, connecting the start pin to somewhere quiet on the primary, and then using just a spare pin somewhere, either on the secondary, or we can even drag back the wire to the primary as well and still be automated. And that is quite a cheap and clever way to implement this shield. Maybe not, as I mentioned, quite as good a results, but can be very good and can be very cost effective if we have a spare pin to terminate to on the primary. Another technique specifically for radiated problems is to use this so-called flux band. This is like an external shield. So it's it's a layer of copper wrapped, this time though not internally inside the core, but externally. And in this case, it can actually be soldered together, and you actually get the best results when you solder this start and the end of this foil together. And what this does is it contains stray magnetic flux lines and prevents them from radiating out into the surrounding environment. And this also acts as a sort of external shield for the windings, and so this can prove quite good for radiated problems. Now this again this shield needs to be connected to a quiet node. It can be usually on the primary side, because often the core is considered part of the primary. So this can be quite a good solution if you're having some radiated problems. But again, it comes with some drawbacks. Usually it's only good for radiated noise. It's quite expensive to implement because it's quite a lot of manual work involved, and then again shielding that or connecting that to the primary pin is a very manual process, and it can also, and usually does, increase the temperature somewhat of the transformer, and even another problem can cause some safety issues if you need some specific creepage distances from secondary pins. So a few drawbacks with that one, but can be good if you're really desperate to pass after, say, the transformer has been developed. Another thing that can be done and can have actually quite good results as well is transformer core grounding. This is where the core, we ground the core, so we basically connect it again to a quiet node. So we have a copper foil tape with an adhesive, conductive adhesive on the other side of that, that's stuck to the core, and then that is connected with a wire then to one of the quiet nodes again, and so that stops the core from being a floating object and grounds it, and then the core then will act as a much better shield for the whole transformer, and also stabilizes the voltage, and so you can get quite good results with this. Again, it's a little bit expensive because again it's a manual process, but it can be a great fix if you're having problems, say, after the transformer has already been developed. This can be added on as a sort of a late extra if you're stuck. Then some other techniques. One thing with SMD components is they usually require some sort of a cap, and that cap is required to provide a flat surface so that the SMD pick and place machines can basically use their suction cups to suck up these components and then place them down onto the PCB. So those caps are often implemented with plastic, but sometimes it can make sense to use a metal clip as well, and that metal clip also can act as a shield for EMC. Can, even without connecting this shield to the ground, it can have some improvements by reflecting some of the EM signals back downwards rather than out into the open air. But for best results, it's better if we can ground this to, again, a quiet node somewhere in the PCB. And some of these clips actually you can get with already tabs so that they can be easily grounded into the PCB, and so it's a very little extra cost, but there is limited availability, and these metal clips are a little bit more expensive than, say, a plastic clip that could be used as well. So yeah, but I guess you get nothing for free in the engineering world either, or at least very little. Then one type of core that can be good to use is these so-called semi-enclosed or enclosed cores. So if this is an EP7 package, or all the EP packages look something like this. So if we look here, we can see basically just core everywhere. So all 5 exposed surfaces are covered with this core, and that core can shield again the radiation from the windings, and also dampen the signals that are radiated out into the air. This is doesn't add any cost, because we often use these type of cores anyway. They're a little bit more expensive than, say, an EE core, but if you're using one anyway, then you get a little bit of EMC improvement for free. And then if you really want to improve that, you can ground this core as well, but a nice way is by using a clip for this, which actually already has some ground tabs built into it, so you don't have to do the manual process, but of course you have to pay a little bit for the extra for the metal clips. And again, these clips are a little bit limited in availability. So that's basically the end of this presentation, and I hope you've picked up some nice tips and some ideas, and basically got the idea that looking into the EMC and the transformer at an early stage is always a good idea. And yeah, if in doubt, you can always ask the people at Würth Electronic Midcom for some help, or if you want a custom, we can do it, and we can take all these considerations into your design, and then hopefully provide you with a transformer that's gives you a good pass in the EMC house. So now I hope some people have some questions for me, and thank you very much for your attention, and I wish you all a very pleasant day.
Attached images are available in most podcast streaming networks. You can find the entire line of Würth Electronic standard and custom transformers available at Würth Electronic Online. The podcast was taken from a recent Würth Electronic webinar. To view the materials and replay the webinar on demand, visit our website at www.we-online.com/webinars, or click the link attached in this podcast. You're listening to Würth Electronics What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Würth Electronic technical specialists who will shine a light on interesting topics like energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Würth Electronics What's Up podcast.